Hello and welcome back. In this video lesson, we're going to look at the behavior of linear systems and what happens when we get zero eigenvalues. So first of all, before we get into it, our system that we're studying, this is a first order, constant coefficient, homogeneous, linear system of differential equations. And once again, the reason this is homogeneous is because we don't have any additional functions of t added on to the end, where we certainly could, but that of course raises some more complexities. This system has only one equilibrium point, and that's the point 0, 0. The way we can find that is if we put 0 in for dx dt and 0 in for dy dt and use technology to solve this for us, we'll only get x and y equal to 0, 0 solutions to it. So we can kind of see that if you plug in 0 for x and 0 for y, the whole right side is 0. And same thing for the second equation. One of the things that we want to get at is there some sort of practical implication behind what the eigenvalue-eigenvector pair means? So first of all, let's consider this system. dx dt equals 2x plus 4y and dy dt equals 4x plus 2y. We could compute its eigenvalues and eigenvectors by observing that the coefficient matrix A will be 2, 4, 4, 2. And as a reminder, it's important that if dx dt comes first and dy dt second, that your x coefficients come first and then your y coefficients. Its eigenvalues and eigenvectors are, here we have the input into Wolfram alpha. We get lambda 1 equals 6, lambda 2 equals -2. So, and we get eigenvectors 1, 1 and -1, +1. And when we put this all together, we'll do this one more time here. We know that the solution to this system will be y equals k1 e to the lambda 1 t times v1, which is 1, 1, plus k2 e to the -2 t times v2, which is the -1, 1 vector. And when we put those components together, x and y, which make up the capital Y vector, is going to be 1k1 e to the 6t minus 1k2 e to the -2t. So that's just us scaling the coefficient by -1. And same thing here, we'll have k1 e to the 6t times 1. And then k2 e to the -2t times 1. So plus 1 k2 e to the -2t. And so that's the solution that we have written down here. Now, when we take a look at the phase plane, here's what we'd observe. And one of the interesting things is we're gonna make this statement without total proof here, but if you look at v1 equals 1, 1, and you think about the origin as where that vector starts, 1, 1 is in the direction of this straight line here. And v2, which is -1, 1, so over to the left 1, up 1, that represents this vector here. Now, if you were to extend those vectors infinitely far in both directions, that eigenvector actually falls along what we call a straight line solution, and same thing with v2. The significance of these eigenvectors is they really form lines that divide the phase plane into 4 behavioral regions. So you see that all these vectors kind of point straight towards the origin here, and from this direction they also point straight towards the origin. So I'm going to delete these eigenvectors here so that these don't get confusing, but everywhere else you can see that the vectors start to curve. So within, say, this pocket, we see that solutions kind of go down and up to the right. And in fact, if we were to draw this infinitely far, we would notice that going in this direction, the solution trajectory would approach this straight line, which is again the line on which one of the eigenvectors lies. And same thing with this other guy. So actually we would probably get something that's a little bit more like this. So I'll draw it as though it approaches, the vectors kind of flow towards the origin and they change directions and those solutions start to make their way out. And same thing here, you can see that the behavior in this pocket is towards the origin and then away from the origin. It doesn't really matter where you look. You can look here, and those do the same thing as well. So that's a behavioral pocket where the solutions flow inward and then back out and to the right. And same thing down here. You can see these vectors kind of cause the solution to approach the origin, but then deviate away. And same thing here, towards the origin and then deviate away. And you can continue drawing curves within these. These are just going to be displacements of one another. And these all these curves that I'm drawing just kind of reference different initial conditions. So my initial condition was there, and my initial condition was there, and so on and so forth. Now, one other thing to note here, one other interesting feature is you see that along this straight line here, all the vectors point inwards. So I'll just draw a little arrow saying that all of those vectors point inwards, and same thing happens here. On this straight line, the vectors point outwards, away from the origin. So I'll draw a green arrow indicating that the flow is outwards, and same thing here, the flow is outwards. And just by drawing the lines on which the eigenvectors lie, and in a second we'll see how that connects to the eigenvalues, and drawing these arrows, you can see that solutions will flow in and then back out. And then here, according to that green arrow, you can almost think about this like a fan blowing a particle. That particle is going to be blown inwards, and then these vectors start to turn and cause that particle to flow outwards. And same thing down here. This vector kind of causes the solutions to flow inwards, but then eventually these vectors have it change directions and follow the arrow here on the green side. So one of the things that we should point out is that lambda 1 is equal to 6 for a v1 of 1, 1. And this is a positive 6, and that's important to note because on the eigenvector 1, 1, and I'm just going to characterize this straight line as corresponding to that eigenvector 1, 1, you see that the arrows point away from the origin. That's a result of this eigenvalue being positive 6. And you'll see why in a second. Lambda 2 is negative 2, and that negative is important to note. V2 equals negative 1, 1. And here we can kind of think about this line as representing or being the line that would be the extension of our eigenvector negative 1, 1. We see that the eigenvalue is negative, which is what actually causes these arrows to point inwards. So positive eigenvalues, solutions flow outwards, out from the solution, or out from the equilibrium point 0, 0. And negative eigenvalues cause solutions on the straight lines to flow into in towards the equilibrium point. So you can kind of imagine if all of these, if these were both negative eigenvalues, all the arrows would point inwards, and all of these vectors would cause solutions to come in towards the origin. If both of these were positive, then you would see all of the eigenvectors having arrows that point outwards, and that would say all the solutions are immediately moving away from that equilibrium point. So that brings up the necessity to characterize and describe, well, what kind of equilibrium point is this? Is it a repeller, attractor? Is it something called a saddle point? And we'll discuss that shortly. So I just want to pull up this applet real quick, so let me do that. So here it is. Here's that same phase plane. This does not have those straight line solutions drawn on there because I superimposed those over it so that you could see the connection, but you can kind of still see those four pockets. You see this kind of straight line behavior here, and you see another set of straight line behaviors going from bottom left to top right. So I've entered in my equations, 2 times x plus 4 times y for dx dt, 4 times x plus 2 times y for dy dt. And I don't know why, but this app can be a little bit clunky. If these dimensions are square, I had to make this negative 0.9 instead of negative 0.1. Negative 1. Because for some reason, whenever I do negative 1 in here, everything goes away. But I noticed that if you do negative 0.9, if you make these non-square intervals, then it works out fine. Not sure why. But inside of here, we can change the initial condition. And you can kind of see what happens depending on where that initial condition starts. And if I move that initial condition down far enough, you see that now it falls into a different region of behavior. And all of these regions lead to the same type of behavior kind of moving along this arc. So like along this arc, we can see x is always decreasing, and y kind of increases as we reach the pinnacle here and then starts to decrease. And so you can see here's a graph of x versus t. X is decreasing all the way down, and the speed at which it decreases depends on the length of the vectors, and that's kind of hard to pinpoint. But y, it starts off negative, it's down here, negative value, which actually comes out to about negative a half or so, something like that. And that, you can see, goes up a little bit. That's this portion of the curve here. And then eventually that drops down because now y continues to increase infinitely. We can do the same thing up here, pick a different initial condition. And you can see the closer I get to that line, the closer this thing immediately starts to hug those eigenvector lines. And from here to here, you can see x is always increasing, and we see that right here. X started off as a negative value somewhere in the second quadrant, but immediately it begins to increase. And again, how that shape looks depends on the size of those eigenvectors. But we see that x is increasing, and then eventually that will be kind of exponential growth. Same thing here for y. Y actually encounters a little bit of a decrease from about y equals 0.73 down to about y equals 0.37. So here you can see 0.73 and about, I'm getting close to 0.47. It's kind of hard to point exactly at that location. We ignore this fourth graph. Don't worry about that. That has to do with options 2 and 3 down here. So actually, if you uncheck that, it'll go away. So needless to say, we can do the same thing over here. And again, we just want to select RK4. The reason this looks so jagged is because it's a worse approximation, but it'll become kind of more curvilinear as you choose RK4. And you can also reduce the step size of it. You make it 0.01, it'll look a little bit more smooth. That's just how often it recalculates those little line segments, because this is all a numerical approximation. So we're ready to make the following claims. The eigenvectors fall along two separate lines that divide the plane into 4 regions of distinct behavior. These are referred to as the straight line solutions. So you could have an initial condition that falls along that straight line, and if it does, it'll just propel at a linear pace outwards. That doesn't mean that the graphs of x versus time and y versus time will be linear, because that depends on the size of the vectors, and those are changing, either shrinking or in this case getting longer and longer. The eigenvalues tell us which way the vectors point along those straight lines. So that's the green arrows I have drawn here. If lambda is bigger than 0, vectors point away from the origin, the only equilibrium point. If lambda is less than 0, vectors point towards the equilibrium point, the origin, which is the only equilibrium point. And then eigenvalues and eigenvectors stated together help us determine where a solution will flow to within any one of the 4 subdivided regions of the plane. So I didn't have to show you any of these vectors. All you needed was just the 2 eigenvector lines and the corresponding arrows here, and you could have sketched without seeing any of these red arrows inside of that plane. So we'll go ahead and take a look at an example now. Oh, and then why does this make sense that solutions are going to flow like this? Well, let's think about what happens in the long run to each of these terms in our general solution. So here, as t approaches infinity, this term right here decays to 0. So this will go to 0 as t approaches infinity. So that's kind of why we can think about the solutions here as coming in a little bit. We have decay in both of our x of t and y of t, because notice they both contain that e to the negative 2t term that will eventually approach 0. It just kind of depends on which of these 4 regions you start in. So the solution gets closer to 0, 0, but then as t gets larger and larger, these guys deviate off to either plus or minus infinity. It depends on the value of k1, whether that coefficient ends up being positive or negative. And this goes to plus or minus infinity. That helps us see that eventually, once that t becomes big enough, and depending on the size of the positive eigenvalue, the bigger it is, the faster it'll kind of curve back out. So now you can see that both x and y are going, in this case, to positive infinity. And here you can see that both of the solutions that start off here are going to eventually deviate to negative infinity. And same here, deviate to negative infinity in both directions. And here they'll both increase to positive infinity. So it's just the values of k1 and k2 that will determine whether these terms are going to have positive or negative coefficients. So with that said, let's consider another example so we can see how this will work. Consider the completely decoupled system dx dt equals 2x and dy dt equals 1y. Find its eigenvalues and eigenvectors and sketch the plane along with straight line solutions. Then sketch its sample trajectory for an initial condition within each of the four regions, i.e. let's do something like this just by using the eigenvalues and eigenvectors. Verify with the Grapher app. Note, we already know the system has solutions x of t equals k1 e to the 2t, because guess what? This is completely decoupled, and if something grows at a rate proportional to itself, then it's going to be an exponential function with that constant of proportionality. Same thing for y of t, that's just going to be k2 e to the 1t. So let's just set this up to get it into matrix form. So we have dx dt equals 2x. Again, list that x term first. It has 0y in it. And dy dt equals, 0x plus 1y. And so that tells us that our A matrix is the matrix 2, 0, 0, 1. So this, even though this is a completely decoupled system, this approach allows us to solve a linear system regardless of whether it's completely coupled all the way down to completely decoupled. So it's a really fast approach to solving these equations. And so lo and behold, we get our lambda and we get our v1, v2. So that means that the y, the solution vector, is going to be k1 e to the 2t v1, and v1, we should note, is the vector 1, 0, plus k2 e to the 1t times v2, which is 0, 1. And notice that when this distributes, the k1 e to the 2t will just end up in the x position. So we'll have 1 k1 e to the 2t, and then y, and then this will have k2 e to the 1t times 0. So we're not going to write any other terms there. Here we'll have k1 e to the 2t times 0 for y of t, k2 e to the 1t times 1 for y of t, and so we end up with exactly what we thought we were going to get. So that's very, very nice, a very, very handy approach to being able to solve these. Now we wanted to sketch the phase plane, so we're going to do that next, and all we really have to do is mark down or plot the lines on which our eigenvectors lie. So let me kind of label this 1, 2, 3, we'll go 1, 2, 3 in the other direction, 1, 2, 3, 1, 2, 3. So the eigenvector 1, 0, that has a 1x component, so a run of 1, a rise of 0, and that tells me that this vector is going to fall along the x-axis. So here's the vector 1, 0 right there. The vector 0, 1 is the vector that lies along the y-axis because x is 0, y is 1. So that's going to be, whoops, a couple of extra things on there that I didn't want. So we'll draw this vector as starting there and pointing straight up. So that means what I can do here is I can think about this axis as being the straight line solution for v2, and I'll do in green, right, because we said that the entire line that this eigenvector lies on is going to be that straight line solution. So that's going to be all the way across right over here. Now, and that's for 1, 0. Now the eigenvalue is positive 2 on the 1, 0 vector, so that means that these guys, these arrows on that straight line are going to point straight outwards this way. So let me take away these two vectors real quick so that we don't get confused about the arrows we're drawing on them. And same thing goes for over here. On this side of the equilibrium point, those trajectories are going to flow outwards. Same thing here. They're going to flow away from the origin because I have a eigenvalue of positive 1, and away from the origin down here because I have it's the same eigenvalue. So here's my equilibrium point, and we see that all solutions, what they're going to do over time is if we imagine that these dictate where the solution goes, these are just going to go outwards and away from the origin. Now they could be kind of curved. We don't really know that based upon just this simple drawing, but we just want to kind of sketch that these solutions are going to go away from the origin. So it depends on where your initial condition is, but you're always going to go to the infinities in both directions. And we can justify that because if we look at k1 e to the 2t, as t becomes infinitely large, this thing either approaches positive infinity or negative infinity, and that ultimately depends on whether k1 is positive or negative for our specific initial condition. Same thing here. As t approaches infinity, k2 e to the t will approach one of the infinities, again barring the sign of k2. So if we want to take a look at the actual phase plane, we should see the same thing. So here we have it. You can see I have dx dt equals 2 times x, dy dt equals 1 times y, and in the phase plane I see, again, those distinct vectors that point straight outwards from the origin right along the x-axis. And same thing over here. The y vectors, it's a little bit harder to tell, but these vectors point straight up, and you can see that the vectors surrounding it have upward components to their vector tips. And same thing down here, these point straight down. And now you can see that although we didn't get the curvature right, you can see that if we start off with an initial condition here, x approaches negative infinity over time. That's this graph here. And again, it looks exponential because our solution is exponential. And y of t, well, y is growing. The y component of these ordered pairs along my cursor are getting bigger and bigger away from the origin, and so y is approaching positive infinity. Over here, similar type of thing, except here both of them are going to infinity. Down here, same thing, but here x is going towards positive infinity. That's this graph. Y is decreasing towards negative infinity, so there's that graph. And then similar type of behavior over here, x to negative infinity and y to negative infinity as well. So pretty cool stuff. And again, just remember you can change your t max if you want this to only show the trajectory for, say, 1 second. It'll still show the entire trajectory here, but it'll only show you 1 second of the graph. So in 1 second, you can kind of see what happens to x, which is this picture, and y, which is this picture over here. And here I've just put that into our document for reference purposes so that we can see that our picture and the actual picture look very similar. So this demonstrates the real power of working with eigenvalues and eigenvectors. These are really complex looking systems, but they have these beautiful features that really help us understand what's going on in the long run. Let's consider one more example. In this case, we're going to end up with actually negative eigenvalues. So dx dt and dy dt are negative 3x and negative 2y. And so we could solve these because these are, again, decoupled. So x of t is k1 e to the negative 3t. Y of t will be k2 e to the negative 2t. And we'll go ahead and prove that by running through this example. So the first thing we need to do is we need to write our system as a matrix equation. So we'll have dx dt equals negative 3x. We have 0 y's in it. dy dt will equal 0x minus 2y. And so our A matrix will be negative 3, 0, 0, and negative 2. So here is the input into Wolfram alpha. Here are our eigenvalues and eigenvectors. So we have y equals k1 e to the negative 3t times v1, which is 1, 0, plus k2 e to the negative 2t times 0, 1. And when we multiply this out, because remember this guy contains x and y in it, so x will be 1k1 e to the 3t, y will be, sorry, negative 3t, y will be 1k2 e to the negative 2t, precisely what we would have gotten if we had done separation of variables on each one of these separately, which is really nice. So again, we'll sketch our phase plane with our two eigenvectors on there. And we see that again, the eigenvectors both lie along the two axes. So I'll go ahead and just plot those there. The 1, 0 vector lies along this axis. And then in a different color, the vector 0, 1 lies along this axis. And because along the 1, 0, sorry, the 1, 0 vector, which is characterized by this entire straight line, the eigenvalue is negative, so the flow will be towards the origin on both sides of the origin. And because of the other one having a negative eigenvalue as well, the flow will be in towards the origin as well. So that means that my picture would look something like this. I'd have the solutions, again, barring curvature, these solutions would go in towards the origin, like so. Both of those are, and you'll see why in a second, once again by looking at the solution. So if we look at this x of t, as t becomes infinitely large, e to the negative 3 times t becomes infinitely small. So x is going to approach 0 as t approaches infinity. Same thing goes here. Regardless of what these coefficients are, y, as t becomes infinitely large, e to the negative 2t will become infinitely small. And so all of the solutions from all directions will approach 0. So very, very beautiful result that we have there as well. And let's again take a look at the phase plane. So here we have that phase plane pulled up again. My Tmax, let me just put that back to 10 so that we get a longer picture of what's going on. But you can see that no matter where these points start, they all seem to go back to 0. And in fact, here is the trajectory for the straight line solution. You can see that as time approaches infinity, on the straight line, the solution just flows in towards the origin in a straight path. Here, these ones are kind of curvilinear, and we don't need to really worry about the curvature right now, but it's going to depend on the magnitudes of the lambdas themselves. So you see that in any case, all the solutions are flowing towards the origin. Now let me just make this a little bit bigger because these are not very interesting. You can see that y, even if I make y equal to 1 and I pick like this outside corner, these curves are very low lying because this point out here, this initial condition is the condition 1, 1, where x and y are both 1. So we should see that in the ty graph that at time 0, we have a y value of about 1, which is what these two boxes show us. And yeah, that seems to check out. And then y is decreasing down to 0. X is doing the same thing. So here at time 0, x is about 1 as well, decays down to 0. If we pick negative 1, they just both start at, well here, y is negative 1, x is positive 1. But if I pick a solution over here, they both start off at negative 1, and they both collapse in towards the towards x equals 0, y equals 0. And then once again, here's that phase plane graph just for reference, just to see that it agrees with what we've already done. So in order to think about what these three scenarios mean, there are actually different classifications. This looks kind of messy, but you'll see in a moment what we're trying to demonstrate. That equilibrium point has one of 6 classifications. For now, we've only looked at 3 of them. So you can see here the blue lines, and this is without loss of generality. These represent the lines on which the eigenvectors lie, but these can be rotated any number of ways. We've seen the eigenvectors lying along the two axes, and we've seen them as 1, 1 and negative 1, 1. There are infinitely many ways those eigenvectors can show up depending on the coefficients of the A matrix itself. But here, where we have what we call an unstable node, notice that the arrows on both of the eigenvectors point away from the origin. So this would be the type of portrait we would draw if both lambda 1 is positive and lambda 2 is positive. I like to call this a source because that agrees with the way we used to draw phase lines, is when the vectors pointed away from, or the flow was away from the equilibrium point. We used to call it a source. but these are often referred to a little bit differently. So I'll call this a source. Here we have all the arrows pointing in towards the origin on both of the straight lines. And so that means that lambda 1 is less than 0, lambda 2 is less than 0. And the very first example we saw where one of them is positive and one of them is negative, here we have arrows pointing away from the origin on the left to right increasing line, but here they flow inwards, and so it doesn't really matter which one you call lambda 1 and which one you call lambda 2, but one of them is positive and the other one is negative. Or where you could reverse these as well. So, or vice versa. That turned out kind of messy, but I'll let you write that in. These other three we haven't considered yet, so I am just going to draw a division between these. These are not ones we need to worry about yet, but that we will revisit. So this block right here is actually going to correspond to complex eigenvalues. So with complex eigenvalues, we get flows that are kind of circular, and that requires sine and cosine. So these are for complex eigenvalues. So I'll just say more on this later in the next lesson. And that basically characterizes at least these three graphs that we've considered here. That in a nutshell shows us anything that can happen with a linear system that has only real eigenvalues. Now there is one last scenario that we'll consider in this video, and that is what if we have an eigenvalue of 0? And when we have an eigenvalue of 0, that essentially means that we're going to have a 0 eigenvector, and that's not going to be very interesting. So in order for us to consider that case, let's take a look at an example. Suppose we have two lakes that has water flowing between them. So here's Lake 1, here's Lake 2, and we have water flowing between them. Lake 1 has 1 million gallons of water, so we'll call this Lake 1. And we'll denote this by, we'll define the variables here shortly, but Lake 1 has 1 million gallons. Lake 2 initially has 2 million gallons. And we know water flows between them. So water flows this way, and water flows back the other way. So there's no foreign source. The only flow is happening between the two lakes. Lake 1 is initially contaminated with a pollutant measuring in at 300 pounds, and Lake 2 is initially free of the contaminant. So we'll define X to be the amount of contaminant in Lake 1. That's measured in pounds, and Y will be the amount of contaminant in Lake 2, also measured in pounds. T is going to be time in days, because you'll see that we're talking about days here. And so we know that X of 0 is 300, so the total amount of contaminant in Lake 1 at time 0 is 300 pounds, and Y of 0 is initially 0 because that one is clean. So you can imagine what's going to happen here. That contaminant is eventually going to distribute itself among the two lakes. So I have a flow rate. Water flows between the two lakes at a rate of 0.5 million gallons per day. So let's focus just on what's coming out of Lake 1. That's going to be 0.5 million gallons. I'll just say m.g. per 1 day. And what's coming out depends on what's inside. So how many since I need my dx dt to be, and dy dt to be in pounds per day, this is not the right units. I want pounds per day, so I have to multiply by pounds over millions of gallons, or per millions of gallons, so that my mg's cancel out and I'm left with pounds per day. Well, how many pounds are inside the lake at any moment? There are X pounds. And how many millions of gallons are there? We'll just, so that we don't have to write out all the zeros, we'll just say we're in millions of gallons. We know that Lake 1 has 1 million gallons in it, so it has X pounds evenly distributed among the 1 million gallons. What's coming out of Lake 2 is, again, a flow rate of 0.5 million gallons per 1 day, multiplied by how many pounds per millions of gallons. Now, in general, there are Y pounds of contaminant in Lake 2, so there are Y pounds distributed in 2 million gallons because Lake 2 has 2 million gallons in it. So the nice part about this is to write dx dt, I have to think about inflow minus outflow. So what's flowing in is this 0.5y over 2, and 0.5y over 2 is just 0.25y. So 0.25y pounds per day are coming in to Lake 1. What's going out? Well, what's going out is 0.5x over 1 pounds per day. So that's going to be minus 0.5x pounds per day. For dy dt, that's going to be similar, but the terms will be the same, but the signs will be switched. So what's coming into Lake 2? Well, it's the 0.5x pounds per day that are leaving Lake 1, and what's going out of Lake 2? Well, that's the 0.25y pounds per day that we have coming out of Lake 2. And so, with that said, we are now prepared to build our system. I'm just going to organize it a little bit better so that we have dx dt equals the x term first, plus 0.25y, and dy dt is going to be positive 0.5x minus 0.25y, giving us a coefficient matrix of a equals negative 0.5, 0.25, 0.5, and negative 0.25. So we compute the eigenvalues of that. Here we have it. And we get lambda 1 equals negative 3/4, lambda 2 equals 0, and v1 equals negative 1, 1, v2 equals 1/2, 1. So we're still going to write our solution in exactly the same way. What we're going to do is we're going to write y equals, or our xy vector equals, k1 e to the lambda 1t, so negative 0.75t times v1, which is negative 1, 1. And then I'll have plus k2 e to the lambda t. Oh wait, e to the 0t, that's just going to be 1, so that's nice. Multiplied by 1/2 and by 1. So that means x is going to be negative k1 e to the negative 0.75t plus 1/2 k2 e to the 0t is just 1, so I'm just going to leave that out. And y equals 1 k1, so k1 e to the negative 0.75t times 1. And then I'll have plus k2 times 1, which is just plus k2. Now, if you observe what's going to happen as t becomes infinitely large, both of these two exponential terms are going to decay down to 0. I forgot my 0.75 there. And so what will be left is the 0.5k2 and the plus k2. Those don't go to 0 because they don't have an exponential term attached to them. Well, they do, but it's 0 as the coefficient. So now I'm prepared to solve my system. I know that Lake 1, x was initially 300, equals negative k1 e to the 0, that's just 1, so negative k1, plus 0.5 k2. 0 equals k1 e to the 0, which is just k1, plus k2. And I get coefficients of k1 is negative 200, k2 is 200. So I plug in negative 200 for k1 in the first equation. I get negative 200 e to the negative 0.75t, plus 0.5 of the 200, which is k2, equals 200 e to the negative 0.75t plus 100. And then the second one, y of t equals e to the negative 200 e to the negative 0.75 t plus the full 200. When I graph them, here's what I get. Along the horizontal axis, I have time in days. Along the vertical axis, I have the amount of contaminant in pounds. The black curve represents what's happening in Lake 1. So it initially has the 300 pounds, but it is decaying over time. Why? Well, probably because it's going into Lake 2. Now, Lake 2 starts off at 0 pounds, but over time amounts to 200. Now, you see that after time 10, for example, 100 in Lake 1, 100 pounds in Lake 1, 200 pounds in Lake 2, that still adds up to the 300 pounds. None of those pounds went away. They're still there. But this should make sense because you might ask, well, why does Lake 2 get 200 pounds? Well, if we look at the concentration, we've basically reached a saturation point. In the long run, Lake 2 will obtain 200 pounds of the contaminant and Lake 1 will obtain 100 pounds of the contaminant. This makes sense since this will lead to a concentration of 100 pounds per 1 million gallons, which is the same concentration as 200 pounds of contaminant to 2 million gallons. So 100 to 1 is the same ratio as 200 to 2. So basically these have just become saturated. Both lakes now have the same concentration. There's no other way for that to become distributed. We're going to wrap up this problem to see what would the phase plane look like with the zero eigenvalue. So here we have that phase plane, and one thing again just to note is for some reason this does not like square dimensions. So my y is set from negative 100 to 100. My x is set from negative 100 to 99. For some reason, if you make this 100, everything goes away. Now, since my initial condition is a lot higher, my initial x is actually, let's see, we said it was 300. Let's try that. And this guy will set to 300 as well. And again, those dimensions go away. I'm not sure why, so I'll just set that to 299 for a second. So you can see here that we had two eigenvectors. One of our eigenvectors was negative 1, 1. So along here, you can actually see that these vectors appear to point pretty straight inwards. And that is because we had a negative eigenvalue, and so along the negative 1, 1 eigenvector, the arrows point inwards. But here we have the 1/2, 1 eigenvector, and you can see that on one side, the vectors point towards it, and on the other side, the vectors point towards it as well. So if I pick an initial condition, like let's say we said x naught is 300 and y naught was 0, we can see what happens along this trajectory over time. Both of those conditions pop up to this point here, which is on the eigenvector 1/2, 1. You can see over here in this box that point is 100 and 200. And if I change that initial condition, we should be able to see that as well. Now, here's the y versus t graph. Let me set this from 0 to, I think the highest y got was 200, so let's go ahead and show that. And then x will go from, negative 10 to 300, because that's where it starts initially. And here you can see as I drag along this curve over time, this x versus t graph, this is dipping closer down to x equals 100 as t gets large. And my y of t is doing the same thing. Now if I move that initial condition around, you can see that that trajectory is still pointing in towards that eigenvector with that eigenvalue of 0. So what happens here is that when these vectors that are being caused by the negative eigenvalue, those are causing things to move inwards, but as soon as they hit that line, with an eigenvalue of 0, those arrows point neither away nor towards the origin, so points along that eigenvector, the line constituting that eigenvector, all of those vectors will simply stop when they hit the line on which that 0 eigenvalued eigenvector lies on. So, and same thing happens over here, doesn't really matter which quadrant. So essentially there are really just sort of like these two pockets of different types of behavior. There's in from the right, in from the left. And just to wrap this up, what I was indicating on that graph is this is the eigenvector right here corresponding to 1/2 1. So that's 1/2 x run to a 1 rise. And this corresponded to a lambda 2 of 0. This vector, this guy here, corresponded to the vector -1 1. And this has an eigenvalue of, I think we found out that to be -0.75. And sorry, that's not lambda 2, that's lambda 1. So you can see that along this vector, the arrows point inwards from both sides of the equilibrium point, which is the origin. And so anywhere along this, you see those eigenvectors kind of clash from both directions. So these are all equilibrium points along this line. And this is the one exception. This is not one of the pictures that we drew in our classification where we looked at the 3 different types of phase planes. This is a very unique situation where you actually end up with infinitely many equilibrium points. It just sort of depends on where your initial condition is. So to wrap this up, conclusion, we see that the line corresponding to the eigenvector with lambda 2 equals 0 attracts the trajectory curves towards it. This means that any trajectories that bump into it will thus be in equilibrium at that particular point. This particular point is specific to the initial condition that we are working with, as we can see in the phase plane. So which equilibrium point our solution goes to just depends on where our initial condition is in the phase plane.